Hello students, so today we will be discussing about the questions of coordination compounds. So before that, we'll just try to understand what are the important aspects you should know before we solve the questions of coordination compounds. So in coordination compound, we represent a coordination compound in a square bracket. Whatever is written within the square bracket is a coordination compound, and outside whatever we write, we call it as a counter ion. Always within a coordination compound, that is within a coordination sphere, we write a metal and followed by the ligands. Ligands are the electron donors which are present, which donate the electron to the empty orbitals of the metal, hybridized orbitals of the metal, and outside whatever we write, we call it as counter ion. It has a simple representation like a salt. So for example, we represent a salt with positive ion and a negative ion. So if you write the complex first, it gets positive charge, and whatever counter ion we write next, it gets negative charge. Or else we can write the counter ion first followed by the complex. That means counter ion is having positive charge and the complex is having negative charge. So based on the charge, we classify the complex into three different types, and those three different types are cationic complex, anionic complex, neutral complex. So if we look here, first we'll try to understand that how we call it as a coordination compound. If you see here, this is a square bracket. Whatever you write within a square bracket is a coordination entity. Whatever you write outside, this is a counter ion. This is coordination entity, this is a counter ion. The first thing what we write is metal ion and followed by ligand. Ligands are electron donor molecules. Similarly, here also if you see, potassium is a counter ion. Whatever you have written within the square bracket is a coordination entity. Iron is the metal, Cn is a ligand. And similarly here also if we consider, whatever we have written within the coordination sphere is a coordination entity. Nickel is a central metal atom and carbon monoxide is the ligand. So overall, all these three are coordination entities, but they differ from one another. So since we have written the coordination sphere first, it is positively charged and the other is negatively charged, hence it becomes a cationic coordination complex. Here if you see, I have written a counter ion first and then the then the complex, and hence we say that it becomes a anionic complex. Next we are having neutral. There is nothing first, second ion. Overall we have written a complex which has no charge on it, and hence it is neutral. Further, we can classify the complexes again into two different types based on the nature of a ligand bonded to the central metal atom. To the central metal atom, if a same type of ligand is attached, we call it as homoleptic complexes. And if different type of ligands are attached, we call it as heteroleptic complexes. Then type of ligand. As I said, ligands are nothing but electron pair donors. So they should have a tendency to donate an electron pair to the available hybridized orbital. And here if we see, in that we have different types like unidentate ligand, didentate ligand, polydentate ligand, ambidentate ligand, chelate ligand. Now unidentate ligand means they can form only one bond by donating one lone pair of electron or one electron pair. Didentate or bidentate ligand means they have two donor atom, hence they donate two pairs of electron to form a bond. And next, polydentate ligand. Polydentate ligand means they can donate more than 3 to 4 pairs of electron to different donor atom. And example is given here is EDTA, tetraethylene diamine tetraacetate ion, which has 6 donor sites into it. Hence it is a hexadentate ligand which we have categorized as a polydentate ligand. And then further, the ligands are also classified, as I said as two types, ambidentate and chelate ligand. Ambidentate ligand means there are two donor sites here. So if you consider NO2 minus, nitrogen also can act as a donor atom or oxygen also can act as a donor atom. At a time, any one can donate the electron pair. So if nitrogen donates the electron pair, we write it as NO2. If oxygen donates the electron pair, we write it as ON. and O. So here oxygen is a donor atom, and in this case nitrogen is a donor atom. Both cannot donate at once, one at a time, and such type of ligand we call them as ambidentate ligand. Next is chelate ligand. Chelate ligand contain two or more donor site and they form ring-like structure with the central atom, and they are more stable than that of the monodentate ligand. So such ligands we call them as chelate ligand. Next is isomerism. So here when we consider coordination compounds exhibit two different types of isomerism. One is structural isomerism, another is stereoisomerism. So structural isomerism are again classified into four types, that is linkage, ionization, coordination and hydrate isomerism, which is also called as solvate isomerism. So all these four have same molecular formula, but they differ in their structural formula. In case of linkage isomerism, necessary condition is that there should be the presence of ambidentate ligand, and this is very important for you to understand. Why? Because usually the questions are repeated onto it. So linkage isomerism arises due to the presence of ambidentate ligand. The complexes have same molecular formula, but the ligating atom will be different. We call them as linkage isomers phenomenon. We call it as linkage isomerism. Next, ionization isomerism. It is due to the presence of exchange of ions with ionization sphere. Here it means that the two complexes have same molecular formula, but in one of the complex, the one which acts as a counter ion, in the another it may act as a ligand, in the another which it acts as a ligand, in one it may act as a counter ion, and such type of isomerism we call it as ionization isomerism. Next is coordination isomerism. It is observed in the complexes having two complex ion. So in one of the complex, your metal may be bonded to a ligand and may have positive charge, and the another metal bonded to a ligand may have negative charge. Both the complexes which change in the charges can be present, and that we call it as coordination isomerism. There is two different complexes with equal opposite charge are bonded here. And hydrate isomerism arises due to aqua ligand, that is due to the presence of water. So it is here we say that they have same molecular formula but differ in the number of water molecules present inside the coordination sphere and outside the coordination sphere. Next is stereoisomerism. So when we consider in stereoisomerism, we consider two different types of isomerism. One is geometrical isomerism, another is optical isomerism. Geometrical isomerism arises due to the difference in the position of ligand around the central metal atom, and optical isomerism arises due to the chirality in the molecule. Chirality means they should form non-superimposable mirror images. Further, you refer your NCERT for IUPAC naming of coordination compounds. So IUPAC naming of coordination compounds, on that also multiple choice questions can be asked, as well as based on Werner's theory. So Werner's postulates are important. So what are Werner's postulates? We'll discuss and then we'll solve the question. So the postulates of Werner's theory are: central metal atom in the coordination compounds possess two different types of valencies. That is primary valency and secondary valency. Primary valency is ionizable, secondary valency is non-ionizable. Primary valencies are satisfied by negative ions, while secondary valencies are satisfied by neutral molecules or negative ions called ligand. And primary valency is non-directional, whereas secondary valency is directional, which gives definite geometry to the complex. So based on this postulates, also questions can be asked. And the last aspect what you need to remember is hybridization. So in your NCERT you have studied four different types of hybridization. One is sp3d2 hybridization, d2sp3 hybridization, dsp2 hybridization, sp3 hybridization, and their respective geometries you should know. Along with that, some of the factors regarding crystal field theory, valence bond theory, as well as magnetic behavior of the complexes should be understood. So based on this, we'll be solving the questions about coordination compounds in the next video. So this is a brief topic which we will be covering. These are the brief topics which we will be covering while we solve the questions of coordination compounds.